let's see what happens to the rate of a reaction if you double the concentration of a first order, a second order, and a zero order reaction. So first let's look at the first order. It's first order because this is raised to the power of 1, and I'm going to go ahead and double my concentration of A. So I'm going to try to calculate rate when the concentration is 1, and I'll try calculating the rate when I double the concentration. So now the concentration is going to be 2. Oops, here, 2. Okay, so 1 to the power of 1 is 1 times K just gives me K. So in the first instant, my rate was equal to K, and when I doubled this concentration from 1 to 2, then I'll say 2 to the power of 1 is 2 times K, 2K. So rate and the doubled concentration is doubled as well. So as I doubled the concentration, I doubled the rate. So that's what happens when you have a first order. If you double the concentration, there, brackets mean concentration, you double the rate. Okay, then next we have what happens if you double the concentration of A in a second order. So same thing, I'm going to try calculating the rate when the concentration is 1, but now it's a second order. And I'm going to try calculating the rate when I double that concentration, still being second order. Okay, so 1 raised to the power of 2, that's 1 squared, 1 times 1 is 1, times K, I just have a single K. So initially, my rate was equal to K. Then when I doubled the concentration, I have 2 squared, which is 4. 4 times K, I have 4K. So 4K is equal to the rate. So I can see what happened when I doubled the concentration of the second order reaction, I quadrupled the rate. And that's what happens when you double the concentration of a second order reactant. So if I tripled, then I'm gonna square that 3. So I'm saying here, I took that double and I squared it. If I had tripled the concentration, then I would have had 3 squared. I would have increased by a factor of 9. If I quadrupled, then I would have 4 squared. I would increase by a factor of 16. So for a second order reaction, if you double the concentration, you quadruple, whoops, P, you quadruple the rate, and that's 2 squared. If you have a zero order reaction, let's check the same thing. So we'll calculate rate if you just have a concentration of 1 and it's zero order, and we'll calculate rate when we double the concentration. So we'll double it to 2, still a zero order. Anything raised to the power of 0 is 1. So I've got 1 times K, and I've got 1 times K. So I can see here, I doubled the concentration, and I had no change in my rate. And that's what happens with a zero order. It's zero order because that reactant doesn't affect the rate. Okay, so that means if you double the concentration of a reactant and there's no change, then you know you have a zero order reactant. What you'll see later means that that reactant is not going to show up in the slow step or before the slow step of the mechanism. So it's giving us a hint on what the steps are of that reaction. Let's try one. So I run my experiment multiple times, and I go ahead and double or triple or quadruple the concentration, and I get the rate from every single one of these times. Let's go ahead and mathematically solve this, and then we'll see how we could talk through it. So I know that the rate law I'm solving for is rate equals K times the concentration of this raised to the power n. Okay, so I will take 2 experiments. I'm going to take 1 and 2. I like doubling things. And I'll plug them in, and I'm going to show you how we can actually calculate how much change we have in the rate if the numbers were not as easy as they are right here. So I'm going to put the larger number over top. So I'm going to look at experiment 2 over experiment 1. So mathematically I'm showing how we can prove what the order of this reaction is. So I've got experiment 2 over experiment 1. So let's go ahead and put the rate law in both cases. So I know the rate of experiment 2 is 0.081. So that's the rate. Oops, here, make that a little shorter. That's my rate, and that's going to be moles per liter second. All right, and in experiment 1, the rate was 0.02. And that's moles per liter second. Okay, and the rate is equal to K times the concentration raised to the power. So I'm going to do K times the concentration raised to the power of N for experiment 2. So that's K times this concentration of 0.2. And remember, the brackets mean mole per liter. So I'm going to go ahead and write it in anyways, just so I can cross out units. Raised to the power of N. And I'll do the same thing with experiment 1. Experiment 1 had this is the concentration, so K times concentration 0.1 moles per liter. Okay, still raised to the power N. Now my favorite part, I get to cancel things out. K is the same. Alright, well that's it. Let's go ahead and go 0.081 divided by 0.02. It's going to be about 4. So 4, and those units are going to cancel out, is equal to 0.2 divided by 0.1. So that's going to be 2 raised to the power N. Okay, so N has to be 2 because 2 squared will be 4. So N equals 2. That means that this reaction, it's going to be second order. So I just got a clue that this reactant shows up twice in the mechanism, either during or before the slow step of the mechanism.